Okay, sorry. Time is running. Yeah.
I will talk about semi-definite programming, and I will illustrate my talk on the example of the max-cut problem. So consider the following problem. We have a graph G with on the set of vertices V and the set of edges is E. Our goal is to divide it into two sets S and T and maximize the number of cut edges.
Without dividing.
No, we don't divide anything. And in the previous talk, we were minimizing the number of cut edges. Here we want to maximize the number of edges. And of course, it's very easy just to minimize the number of cut edges. This is the classical min-cut problem. So our objective
I'm sorry, I'm already lost. In the previous talk we divided by something, and that's what important. I see. And also minimize, and here maximize.
Here I maximize.
Okay. Delicate things. Yeah.
So let's first try to construct an algorithm.
It's cheating that. In the previous talk you convinced us that a good goal is to minimize. Now you try to convince to maximize.
Many different objective functions. So how can we solve this problem? Let's just try a greedy algorithm. So let our sets S and T be n set initially, then pick one vertex after another and put it into S or T. So we put the first vertex in S, then, so what shall we do next? We have another vertex. Where should we put it? So we look at the set of vertices adjacent to U in one set and the number of vertices adjacent to this vertex U in the other set, and if there are more adjacent vertices in T, like here, then we put U into S, otherwise we put U into T.
Yeah, so if, for example, if we just divide the vertices in to classify the vertices in V to S and T with probability 1/2, then each edge will become a cut edge with probability 1/2.
Yeah.
So there exists a cut of size 1/2, yeah?
Right. This is the second algorithm. So what Sasha said, we can just randomly put every vertex either in S or T, then every edge is cut with probability 1/2. So this algorithm reduces the solution that has at least total number of edges over 2, and therefore this number is, of course, is at least optimal value over 2. So you want to express this number in terms of the optimum.
This only in the expected sense, right?
Yeah, so in expectation you will get optimum over 2. This algorithm can be de-randomized as well, and I mean with the constant probability we will get optimum over 2, or almost optimum over 2. Another approach is just,
what do you get in the first case?
The greedy algorithm, and here at each step we add one vertex and we add several edges, and we cut at least half of them, right? So at each point of time we add some edges and at least half of them are cut. Therefore the total number of cut edges is at least half of all edges. So here our guarantee is also number of edges over 2, which is again at least optimal over 2.
Yeah.
We can try other.
Yeah, by the way, the first algorithm is just the randomization of the second one if
Right.
you take conditional expectations.
Right.
So, yeah.
That's true.
Yeah. Yeah, and what now? So our goal is to get better constant. Yeah.
We want to get something better than 2 here. And this was a long-standing open question in theoretical computer science. For instance, we can apply linear programming, and I don't describe this approach, but you will get also our tools. And now I will describe the algorithm of Gomez and Williamson. Which achieves much better approximation during this is 1993 actually. So the idea is the following. Consider, in a sense, a physical system. Let's, for every vertex, let's consider, say, a real line and 2 points, -1, 1. And let's put every point either into this point of space or this. So for every vertex I, let's introduce variable, its coordinate ui. And let's
between -1 and 1, yeah?
For now it's either -1 or 1.
Mm-hmm.
And now let's say that our vertices, our particles, interact. So the energy of interaction of 2 points is equal to 1 if they are located at different points. And it is equal to 0 if they are located at the same point. Now, our objective function, actually, it's better to have -1 if you want to have a good physical analogy, but we will, for convenience, have 1 here.
Mm-hmm.
So, now our objective function is the number of edges between S and T. But this is just equal to the total energy. So sum of overall I and J connect maybe to avoid confusion I will rename energy and denote it by H. Sum over all edges IG connected with an edge, energy I and T, and our goal is to maximize the energy. So in a sense to find the equilibrium state of the system. And so this problem is exactly equivalent to the original. So it's also anti-high.
Yeah, but there is not much physics if they are discontinuous.
This is discontinuous, yes, that's true.
I
don't
understand.
Sorry. What you don't understand?
How the is the random value or not?
No. Actually, nothing happened, so there is nothing to understand.
Yeah, nothing to understand.
So maybe just wait a bit and something happened and you will understand.
For a moment, I can forget that we have introduced some random variable.
No random variable. Just instead of saying that this is an S, we say that this point is placed in -1.
Mm-hmm.
And instead of saying that we want to have maximal edges between S and T, we say that we have to maximal edges which are placed in the different points. Mm-hmm. And H is the sum of this value. So just we count the number of points placed in the different places. So, so physically it's rather strange because it's a kind of interaction between points only if they are connected by an edge.
Oh, okay. No, it's just some kind of
points interact in this
Forms
way.
or something, so it's not that surprising. They connect by something. And if they're in the same point, then with a rope, elastic rope, if they're at the same point, there is no tension, so the energy is zero, otherwise it's for some positive number.
But then it's, we look for a state of a maximal energy,
Yeah,
which has no
what I
physical
said.
minimum.
Actually, we need to have minus here.
Yeah.
But it's
So
just
this
convenient.
means
This
that
is not the
that-
energy, this is the minus energy.
Yeah, but this means that the points, the elastic string tries to.
Yeah, but it can be like.
Yeah.
Spins in this position has less energy than in this position.
Yeah, okay, but it's only what I'm saying is what is strange is this happens only for if there is an edge. So for spins you cannot say that there is an edge or not. Okay.
Imagine a grid, square grid, and spins are interacting only within neighbors.
Okay.
Нет, можно пружинку поставить между ними. Тогда будет все работать.
Да. Хорошо, ладно, давай
Не
дальше.
между всеми.
Я понимаю, да. Но со спинами так не выйдет.
Со спинами, наверное,
Okay, whatever it is. Yeah.
But of course, the other strange thing that we restrict our points on our like particles only to 2 points, -1 and 1. Now let's realize this condition and instead require that they just lie on a unit sphere. So every UI is a unit vector. And moreover, we don't impose any restriction on the number of dimensions. So let's say all our points lie in n-dimensional space.
Sphere is a normal Euclidean sphere.
Normal Euclidean sphere, yeah. Absolutely. And then it turns out that we can solve this problem. So we can maximize this objective function subject to this constraint that all UIs are unit vectors.
Yeah, but you should define objective function if now it's not 0 and 1, but there is some formula.
So let's define. So that's true. I forgot. UI minus Vj squared, the squared Euclidean distance divided by 4. And this definition coincides with this definition if UI and Vj are only -1 or 1.
This is why 4 is needed, yeah.
This is why 4.
Yeah.
Yeah. And now we have this objective function, some these energies, and it turns out that we can solve this semi-definite problem. And intuitively, just because we have many, we can continuously change our system. So in this case, we have a discrete system, and we couldn't continuously change the values of our variables. And here we can continuously change the values of our variables and increase the objective function. So I will explain why we can solve it in no time, but I think it's pretty. It's not that surprising. So now, we solve this problem. We get vector our vector ui. So for every vertex I, we get ui. And now we want to produce a good card. So what we do is very simple. We consider our sphere. We take a random n-1 dimensional hyperplane, and this hyperplane divides the space into 2 half spaces. Let S consist of those vertices for which UI lies in one of these half spaces, denoted the half space 1, and let T consist of those vertices for which UI lies in the other half space. Now let's analyze the probability that a particular edge ij is cut.
But a stupid question. Imagine we have a sphere of high dimension and we take two random points. What is the typical distance between them? Just two? Almost two, or what? Just take random points of sphere.
Square root 2
How do you get UI?
with very high concentration.
How do you get UI?
So this I didn't explain, I just said that it's possible to solve this problem, and because here we can continuously change the values of UI.
No, it's not something which we should understand immediately. It's a whole theory, I guess.
It's not obvious at all.
But still, is it true that we obtain a semi-definite program?
Yeah.
Whatever
is it true?
it is.
Okay, but is it true that there is a polynomial time algorithm to solve semi-definite program?
Yeah, except that we resolved it with any precision.
Okay, so combining these two statements in which
Yeah.
we can believe, we obtain the result.
Yeah, especially we can believe if we don't know what is a semi-definite problem. But okay, let's continue. No,
Yeah.
it's another part of an interesting part. So we should concentrate on something. So let's concentrate on this. Yeah.
You were going to please explain whether you have square in the definition of energy.
Why?
And when to use just subject without square.
So
No, it's for example, there is a polynomial.
program, but I will, after I explain this algorithm, I will say a couple of words why I pick this objective function, why this is a semi-definite program, at least if I have some time.
Yeah.
So roughly speaking, all the objective functions and all the constraints should be linear in the inner product of variables. Linear functions depending on the linear inner product. So let's look at I and j. What is the probability that this Cartier plane separates ui and vj? So we can consider the plane passing through ui and vj. So let's consider the plane that passes ui and vj. And the intersection of this random hyperplane with this two-dimensional plane is just a line, right? And this is a random line. The probability that this line separates ui and vj is proportional to the angle between ui and vj. So what we get, that probability that the edge ij is cut in our solution equals to the angle between ui and vj divided by pi. So here we have if this line crosses either this angle or this angle, then two points are separated. If it crosses this angle, then the points are not separated.
Is it in 2 dimensions or?
This is a two-dimensional picture.
Okay.
But of course, if you take a random plane and intersect it with this two-dimensional picture, we get a random line, because so this random line is uniformly distributed.
Yeah.
Okay.
So we can compute only in 2 dimensions. We don't.
Really?
Yes.
No, because it's a random. No,
So this is a plane that passes through the origin UI in UG.
Points are fixed now.
You're not looking at anything.
There are 2 points on the sphere.
Okay.
We compute the probability how random plane.
Multi-dimensional.
Multi-dimensional.
Okay.
We want to find the probability for a random plane but let's first intersect this random plane with the 2-dimensional plane. Of course, everything is determined by this intersection.
Passing through U sub I and U sub J.
Yeah. So this line is also uniform.
Okay.
Yeah.
So what is the angle between UI and UG? Let's use actually the cosine law. So we have that UI squared. That's right. UI minus UJ squared. The distance between UI and UJ is equal to UI squared plus UJ squared minus 2 times linear product of UI and UJ. And this is equal to cosine of the angle. And UI and UJ are unit vectors, so we have this expression is equal to 2 minus 2 times cosine of this angle θ, this angle. And so
we get an unpleasant arc cosine here.
Yeah, we get arc cosine. So we get divide everything by 2. Arc cosine of so fine. Right.
Okay.
Now we want to say we want to express this probability in terms of this contribution of this Hij. So we can say that this value phi is equal to cosine of 1 minus Hij over 2 over 2 times Hij. And now we are doing something computational. So now we say that this expression is always some constant times the Hij. So note that but this constant just is equal to the minimum of this ratio. So we can take this constant and define it as the minimum of the ratio between our cosine of 1 minus 2t and t where.
Okay, just you can draw the graph of arc cosine and show the line which goes here.
Yeah.
Hey, it doesn't help anyway. This formula
Draw the graph. We will.
of arc cosine. Is it possible for us to draw a graph of arc cosine?
No.
No, but Yury can. I believe in you.
Actually, we want
No, just of arc cosine x. Can we just draw a line?
just
Arc cosine of x without anything. Just basic arc cosine for us to remember what it is.
arc cosine.
X. Can we draw the graph? Arc cosine of 0 is of 1 is 0, yeah?
Arc cosine.
Of 1 is 0, and then it goes like this. Yeah. Yeah, and what you do now, you draw the line. This C is just the line which goes like this, yeah? You will just let me draw the C.
Maybe here change the parameter.
Here is the C, yeah?
Yeah.
Okay, let's continue.
Yeah.
Yeah. But what we do with this, we have some constant which we don't like.
We just compute it numerically, whatever we differentiate, compute the value numerically, and get this constant.
Yeah, but now we have what fraction we lost due to this. We want to get some close to optimal, but now because of this C.
Yeah. So just like because of this, so depends what. So if this ratio is C, then we have C over pi here. The ratio is C over pi. So we get that the probability that we cut an edge is proportional to this contribution of this edge to the objective function. So
yeah.
the expected number of cut edges is proportional with this C or C over pi to the objective function. So the number of cut edges in expectation is greater than or equal than C over pi times the value of the SDP program, and the value of the SDP program is at least the optimal value. And if we numerically compute this C over pi, that what we get is 0.878. Of course,
Instead of 1/2.
Instead of 1/2.
So we get a significant improvement.
Yeah.
But we are just somehow lucky. But you can expect any answer for this computation with cosine. It can well be below 1/2 probably, or some philosophical reason why it should be above 1/2. Why this algorithm should be philosophically better than.
But that would go through